Inclined plane is going to be the topic of this lesson in my new general physics playlist, which is going to cover a full year of university algebra-based physics. Now, the rest of this chapter is dedicated to all application of Newton's laws. We're going to be solving numerous examples of the common types of problems you're likely to encounter. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So inclined planes problems. These are going to be a common Newton's laws of motion kind of a problem you're going to encounter somewhere along the way. An inclined plane is simply nothing more than some sort of tilted surface like a ramp. And you're going to have some object either sliding down that ramp or at rest on that ramp, or maybe somebody's going to push it and try to make it slide up the ramp, something of that sort. And these inclined planes are typically defined as being some angle theta above the horizontal. That's the angle of the ramp, if you will. What we're going to find out is that we're going to treat these as any other Newton's laws of motion problem. We're going to set up a free body diagram. It's typically going to be a two-dimensional problem. We're going to set up the sum of the forces in both dimensions, the net force. It's either going to equal 0 if there is no change in velocity in that dimension, or it's going to equal ma if there is a change in velocity and an acceleration in that dimension. All right, but it turns out we're not going to use the normal x and y axes for such a problem. It's going to be much more convenient to kind of redefine our axes, as we'll see. But let's start with the free body diagram. So what forces are acting on an object, let's say, that's on this ramp? And whether it's at rest there, or it's sliding down, or it's being pushed up, what forces are going to be present no matter what? Well, we've definitely got the object's weight, and gravity points straight down. So that's its weight, mg. And then we've got a contact force between whatever this mass is and the incline itself. And if you recall, the normal force is always the perpendicular contact force. It's perpendicular to the surface. And so in this case, that's going to point off this direction. So it's perpendicular to the incline itself. So you're always going to have these two forces. Now, additionally, you may have something like friction. And if you recall, friction always opposes the motion. So if it's sliding down the incline, you might have kinetic friction pointing up the incline. If somebody's sliding it up the incline, pushing it up the incline, then you might have kinetic friction pointing down the incline. Or let's just say it's at rest and it's just sitting right there. In such a case, then you might have static friction actually is the thing that's keeping it from sliding down the incline, and so static friction would be pointing up the incline in that kind of a situation. So those are the common examples where you might also have friction, but it's also common to see problems where you're told it's on a frictionless surface, this incline. And in such cases, then we wouldn't have friction. But you're always going to have at least these two forces. Now, in such a case, though, notice in any kind of consideration we've made here, this object's either going to be sliding down the incline or up the incline. Or it might just be at rest, I guess. So there's a case to be made for situations where it's either at rest or it's sliding at constant velocity. So in such cases, there'd be no acceleration. But there's other cases to be made where it might be sliding down and accelerating down the incline as well, as a common example. So in such cases, then the net force is going to point down that incline, and that's pretty common. Well, typically you want your net force in a lot of your Newton's laws problems, if possible, to point in the direction of one of your axes. And this is not always going to be possible, but in every example we've looked at so far, it has been. When we dealt with gravity. Well, gravity's in the vertical dimension, and so having that as one of your orthogonal perpendicular axes was really convenient. Well, in this problem here, if this is the most likely dimension where we're going to see acceleration, well, that's not one of our normal x and y axes, but it is now. We're going to define that as one of now our new orthogonal, and orthogonal is just a fancy word for perpendicular axes. And then the other one here is going to be this one right here. And so we can see that the normal force is going to point directly in one of the dimensions, one of the axes we're going to consider now. And I'm going to call this the new inclined plane x-axis, and this is the new inclined plane y-axis. But we can see that the object's weight due to gravity here doesn't point completely in the x or y axis, and this is the first place students kind of encounter some problems. So we're going to have to break it up into components of these new axes. So we're going to have to figure out where this angle theta is, which is usually kind of something that gives us a little bit of fit. So what we're going to do to figure this out here, we're just going to extend the weight down here a little bit. And then we can see opposite that normal force is going to be a component of the weight here. And then down the incline here is going to be a component of the weight as well. And there's our new axes. And the question is, what are those components? Well, I made sure to pick a ramp here that wasn't close to 45 degrees, because then it would be like an isosceles triangle, and it would be tough to see where this angle is on this particular triangle as well. But in this one, you can kind of see it, but you're going to need more than just to kind of see it. You got to verify why this angle theta is this angle theta right here. Because once we see that, then we can decide whether we need to use sine or cosine to get the different components. So how do we kind of define that that's there? Well, let's take a look here. So let's say I take, and let's do these two. So let's say I take these two and make an angle theta between them. Now, as long as I take these and rotate them together, that angle theta between them is constant, as long as I'm moving them together. Well, what if I don't move them together? What if I rotate this one 90 degrees, and then I rotate this one 90 degrees? Well, as long as I rotate them by the same amount, then it should still be the same angle theta between them. So I don't actually have to move them at the same time, but it's still going to work. One other thing you need to note here is that I kind of showed the angle here, but let's just say I extended this over a little bit. Well, this angle theta right here is equal to the other angle on the other side. Those are vertical angles you might remember from your geometry days. So I just want to point that out. So we've got some props here to help us out with this. So we're going to have this angle again between these two. And what we're going to do is we're going to rotate both of these boards by exactly the same angle. And so the first thing we're going to do is we're going to rotate this board right here by 90 degrees, making it vertical. And then we're going to take this board right here and multiply it 90 degrees, and now it's with the normal to that surface as well. And so the angle between these boards, either on the top side or the bottom side, should be exactly the same as it was when it was right here, because all I've done is rotate them by the same degree. And so as a result, the angle between them right here is theta. So then the angle, once I rotate them both 90, which is here, and then on the other side with the vertical angle, is also theta. Now here's the deal. Maybe you're like, Chad, I struggle to see that. Fair enough. Memorize it then. So because, and the truth is, I'm gonna want you to memorize this anyways. Even if you can see this, it's going to be much faster if you kind of recognize, oh, inclined planes, common type problem. I should recognize that it's this angle that's theta. And in fact, we're going to take it a step further in a second, as we'll see. So if we look then, so a couple things we should realize, that this part right here is opposite angle theta, and that's again the part going down the incline. And for the component that's opposite the angle theta, that's the sine function. And so down, this is going to equal mg sine of theta. This is the adjacent side right here, and so that vector component is going to be mg cosine theta. All right, so now we've broken it up into components. Both these components are now in our new set of axes, and what I recommend is that you don't have to drive this every time. I'm going to ask you to actually recommend you memorize this. So let's go back and redefine some things now. So we've got on our new y-axis, the normal force points directly in that positive new y-axis. Life is good. Okay, and directly opposite that normal force in that new y-axis direction as well is mg cosine theta. And then pointing down the incline right here is mg sine theta. And so now instead of drawing, this is not a proper free body diagram, by the way. It's the one where the weight has already been broken up into into components of the vector. So, and again, we don't want the weight by itself. That's not going to be in the direction of either of our new axes. And so, but here, broken up into components, and this is tricky now, because this is kind of like our new inclined plane x-axis, but we're using the sine function. Normally we think of the x component as using the cosine function, not for the inclined plane. So same thing here, the new y component is using the cosine function. Normally in our axes, the y component is using the sine function, again, as long as we're using the angle relative to the x-axis, but not with inclined planes. It's going to be backwards. So the y component of the weight is going to use the cosine, the new x component of the weight is going to use the sine. And again, this is not the true x and true y, just kind of my inclined plane x and inclined plane y dimensions as defined. And now the problem is much easier. And we can do the same thing we've done in the past. So we can do the sum of the forces in the y direction. And in this case, there's no acceleration or even motion in this new y direction. So it's going to add up to 0. And we've got a normal force. So pointing up, so I'll make that the positive direction. Mg cosine theta pointing more downish, so I'll make that the negative direction. And so Normal force minus mg cosine theta equals 0. And we can see pretty quickly that the normal force actually has a magnitude of mg cosine theta, and that's pretty common. So, and you're probably going to even get to the point where you're probably just kind of making that assumption from the get-go that this normal force is probably going to have that magnitude right there, right off the bat. Same thing in the x direction. So we've got the sum of the forces in the x direction. Now, if this object's at rest, well, then that's going to equal 0. But if it's sliding down the incline and not at constant velocity, well, then the sum of the forces would equal ma in that x direction as well. And in this case, the only one we've got is mg sine theta, but if we had any sort of frictional forces, we'd have to worry about those as well. Now, typically, up the incline is going to be more of the positive direction and down the incline more of the negative direction, or vice versa. You could look at this as more to the right and that's positive, and this is more to the left and that's negative. It's really up to you. So, but the big thing is this: if you define down the incline as positive, so, well, if the object is accelerating down the incline, then you got to make the max positive as well. If you decide to make sliding down the incline negative, then you have to make the max, if it's sliding down the incline, also negative. So that's kind of the key. I personally like to think of, going to the right as positive and going to the left as negative. That's my choice. It's kind of analogous to left and right. And then going up in the normal force direction there is positive and this negative. But, that's pretty typical. But it really is kind of arbitrary to a certain extent. These aren't the true x and true y anyways. So, but if I'm kind of making them analogous to x and y, then that's probably how we should do this. All right, so if I've made mg sine theta positive, then the overall acceleration is also in that same direction, so it's also positive. And so now they're just both positive terms. Great. So, and again, if we had friction, then we might have to subtract friction off minus that frictional force going back the other direction. It always opposes the motion. All right, so this is kind of the normal setup. And again, if you've got any additional, say, frictional forces, or if somebody's pushing something up the incline and we've got to factor that in, things of that sort, we'd add those in. But this is kind of where it starts. Let's take a look at a few examples. All right, first inclined plane problem we're going to look at here. So a 10.0 kilogram object slides down a frictionless plane inclined 30.0 degrees above the horizontal. What is its acceleration? All right, so first thing we'll do, just like normal, set up a free body diagram. But again, instead of actually, putting the normal force on there and the weight, which is proper, if you're asked to draw the proper free body diagram, yeah, you should draw the weight straight down. But what I'm going to recommend you do, if you're actually just solving this and aren't being asked to actually show your work and provide the actual free body diagram, is to jump straight ahead to breaking up the weight into components. And again, we've got one component here, that's mg cosine 30 degrees. And then we've got one component down the incline as well. That's mg sine 30 degrees, just like we've kind of laid out over here. And that's going to help, quicken our ability to solve this immensely. So we want to know what's the acceleration down the incline. We're told it's frictionless, there's no friction. This is the entire free body diagram with all the components defined in terms of the axes we want to use. And we want the acceleration down the incline, so we want to start with that axis right there. I like to call that my inclined plane x-axis, and so some of the forces in the x direction, that's where we expect to have an acceleration, and so it's ma, not 0, x component of ma anyways. And in this case, the only force acting is mg sine of 30 degrees, and that's going to equal m times the acceleration acceleration in the x direction. This inclined plane x direction anyways. Cool, if you notice, one thing's going to fall out of this equation, and what is that? That is the mass, and it turns out the mass doesn't matter. Now, if I told you I was dropping a bowling ball in a vacuum, so there's no air on the surface of the Earth, what would be the acceleration it should drop at? Well, 9.8 meters per second squared. If I told you I was dropping a feather in a vacuum, again, there's no air, near the surface of the Earth or on the surface of the Earth, what would be the acceleration of the feather down to the ground? Well, it would still be 9.8 meters per second squared. We learned earlier that gravity doesn't care what your mass is. Its acceleration is 9.8 meters per second squared as long as you're to the surface of the Earth. The only reason we observe something different is due to air resistance for this bowling ball versus feather. But if you do this in a vacuum, that air resistance goes away and they will accelerate down to the Earth with exactly the same acceleration of 9.8 meters per second squared. Well, we shouldn't be surprised. It is gravity that is pulling something down this incline as well. And so we shouldn't be surprised too that as long as there's no drag forces. In this case, instead of air resistance, we consider friction. But if it's on a frictionless surface, we shouldn't be surprised that the mass doesn't matter. It wouldn't matter if it was a big box or a small box sliding down that incline, it would still have the same acceleration, and the mass falls right out. And so if we look here, the acceleration here, it's just going to equal g sine 30. Well, g is 9.8 meters per second squared times the sine of 30, which technically something we can do in our head because it's 1/2. And we see that this acceleration is equal to 4.9 meters per second squared. And in this case, we've got 3 sig figs on both numbers, so we should add one more 0 on there to get 3 sig figs, but 4.90 meters per second squared. Now, you might be like, Chad, we never set up the other equation. You're right, we didn't. We started with the one we knew we were going to have to use because that's where the acceleration was when we were being asked for that acceleration. Had we needed more info, we would have then proceeded to set that one up. And we would have just had normal force minus mg cosine 30 equals 0. And we could have figured out that the normal force had a value of mg cosine 30. We just didn't need to for this problem. Let's take a look at the next one here. A 10.0 kilogram object is at rest on a plane inclined 30.0 degrees above the horizontal yet again. The question now is, what is the force of friction acting upon the object? And second part of the question, what is the coefficient of friction in this case? Okay, so first of all, we're told that the 10.0 kilogram object now is at rest. And if it's at rest, then there must be some sort of opposing force going up the incline. And so there must be an opposing force that's perfectly canceling this out to allow it to be at rest so that there's no net force in that dimension. Well, in this case, we know that to be friction. So, and in this case, it's going to be static friction if it's at rest, not kinetic friction. So when we're being asked for the coefficient of friction, notice it says be careful, we'll figure out why that is in a second. So when we're being asked for what is the coefficient of friction, it's the coefficient, therefore, of static friction. So, and we're just asked, what is the force of friction acting upon the object? Okay, well, let's set up some new equations here. Once again, we'll just start with the dimension that we need. So we've got sum of the forces in the x direction is going to equal max. No, again, we're told this thing's at rest. And if it's at rest, there's no acceleration. And so the sum of the forces now are going to equal 0. Okay, but now we got 2 forces. We've got one up the incline, one down the incline. And again, I like making these positive and these negative. You might do it the other way around. The math works out either way. And so in this case, we're going to have mg sine of 30 degrees minus that force of friction equals 0. And in this case, again, we're trying to find what is the force of friction and what is the coefficient of friction. Well, there's the force of friction. And so if we solve for that, we'll get the force of friction is equal to mg sine of 30 degrees. The mass matters now, so that's 10.0 kilograms. Gravity is 9.8 meters per second squared. Sine of 30 is 1/2. And there's our force of friction. So notice 9.8 times 10 is 98, and then times sine of 30, which is 1/2, takes it down to 49, and that is 49 newtons. Once again, we haven't had to set up the sum of the forces in the inclined plane y direction to solve that, but we will for the second half of the question. The second half is what is the coefficient of friction? And again, here it says be careful. We'll see why. But what is the coefficient of friction? In this case, we know it to be static friction. Well, in this case, we know that force of friction is equal to mu times the normal force, and if it's static friction, it's the static coefficient of friction, or the coefficient of static friction. All right, so that's what we've got. We know that the force of friction is 49 newtons here, but we don't know the normal force yet. So, except that that's what the sum of the forces in the y direction are going to be for. And once again, there's no acceleration in this inclined plane y direction at all. This thing's not jumping off the incline or anything like that. So sum of the forces is equal to 0 in that dimension. We've got 2 of those forces. We've got the normal force in the positive direction, mg cosine 30 in the other direction. And so I'll make that one negative. So, and it's equal to 0. And from there we can solve for that normal force so that we can plug it in for our frictional force and solve for that coefficient of friction. So here it's going to equal mg cosine 30, which again is 10.0 kilograms times 9.8 meters per second squared times cosine of 30 degrees. And we'll let the calculator help us out on this one. All right, 10 times 9.8 times the cosine of 30 is going to get us 84.87, which I'll take and round to 3 sig figs based on the numbers that are given here. 84.9 newtons. So, and the truth is, it's really the final answer I care about. So maybe even carrying out one more digit here wouldn't be the worst thing in the world, because that's not actually the ultimate answer we're looking for. So, but in this case, if we rearrange this and solve for that coefficient of static friction, we can see it's going to equal the ratio of the frictional force to the normal force, or so we think. Let's take a look. All right, so frictional force we figured out was 49 newtons. Normal force we just figured out here is 84.9 newtons. We'll get that ratio. So in this case, 49 divided by that last answer is 0.577. Okay, now the question asks, what is it equal to? And there we go. But what was the whole point of the whole be careful phrase? That was part of the question. Well, here's the deal. This is not necessarily what it's equal to. And if you recall, the equation for the force of static friction is specifically that the force of friction maximum is equal to that. And the question is, are we at that maximum? Well, we don't know. So, and it could be that we could incline this a little higher and that thing would still not slide down the incline. Are we at the point right where it starts to slide down like we saw a couple lessons ago? Maybe, maybe not. So actually, I guess that's the last lesson. Don't know. So we don't know if we're there or not. So here's the deal. We know that our coefficient of static friction is big enough to keep this thing from sliding down. And it has to be at least this big for that to be possible if we're at the maximum. But it might be bigger than this as well. And so what we can ultimately say is that our coefficient of static friction is greater than or equal to 0.577. It's got to be at least that big to keep this lovely mass at rest and not sliding down the incline, but it might be bigger than that. We might not be at the maximum. It's at least 0.577. All right, the last incline plane problem we're going to take a look at and solve says an object slides down a 45-degree incline at constant velocity. So bells should be going off in your head when you hear that phrase, constant velocity. And the question is, what is the coefficient of kinetic friction between the object and the incline? Okay, so this thing's actually sliding, but at constant velocity. Now, if we start here, again, you've got your normal force coming off right there. Right opposite, you've got a component of the weight of mg cosine theta, 45 in this case. And then down the incline, mg sine 45. And again, my preference is that you start here. Again, this is not the real free body diagram. And if you were simply just asked, hey, show the real free body diagram, well, then you wouldn't draw this. You'd draw the mg straight down. So, but we also got to infer one other thing, is that this thing's sliding at constant velocity. If it's at constant velocity, it means there's no acceleration. The sum of the forces adds up to 0. And I can see how that would be true here. These must be equal in magnitude, opposite in direction, just like Newton's third law tells us. But what's going on here? Well, there must be a force in the opposite direction that's equal in magnitude, and it's going to be friction. And in this case, it's going to be kinetic friction. The whole question's asking us, what is the coefficient of kinetic friction? We're not told it's frictionless, and we're being asked for a coefficient of kinetic friction. So there must be friction opposing the motion. So it's sliding down at constant velocity. So, but that also tells us that these are going to be equal in magnitude, so just opposite in direction as well. All right, so set up our sum of the force equations now. So they're both going to add up to 0 as the case may be. And since we want to deal with the coefficient of friction, which is going to be this one, we'll definitely deal with the x first. We'll deal with the y if we need it. And in this case, we've got mg sine of 45 degrees minus that force of friction, kinetic friction, equaling 0. But we want to solve for the coefficient of kinetic friction, so we have to go a little bit deeper here. So we're going to have mg sine of 45. And again, force of friction is mu times normal force, so mu kinetic times the normal force equals 0. And here's why we need that other equation, because we don't know the normal force. And we want to solve for that coefficient, we need to know everything else. Well, we know the mass, we know gravity, we don't know the normal force yet. So, but we can kind of infer it's going to equal mg cosine 45. So, and how would we get that? Well, from the sum of the force in the y direction. So the normal force is we'll think positive, minus the mg cosine 45 adds up to 0, and so that normal force must be mg cosine 45 degrees. All right, so from here, we're going to substitute that in right here. We're going to get mg sine of 45 degrees minus that coefficient times mg cosine 45 degrees substituted right in, again, equaling 0. And we'll move this over to the other side. So mg sine of 45 degrees is going to equal mu times mg cosine 45. And then we'll divide through to isolate mu by itself. And it's equal to mg sine of 45 degrees all over mg cosine of 45 degrees. Well, mass didn't matter. Gravity turns out doesn't matter. So because it's at 45 degrees, well, it turns out sine of 45 and cosine of 45 are both equal to the square root of 2 over 2. And so our coefficient of kinetic friction here is simply equal to 1. And obviously at this point we'd have to make it 1.0 to be 2 sig figs. So my bad, but it's equal to 1.0. And once again, the mass didn't matter, gravity didn't matter. It all fell out of the equation as it was. Now, if you found this lesson helpful, would you consider giving it a like? Happy studying.